Welcome back to another video with us here at LMDN STEM Academy. In this video, we'll be providing a set of detailed solutions to the CAPE Chemistry Unit 2, Paper 2 from June 2024. So now we're starting out with Module 1. So here's our question 1. Question 1A says that a hydrocarbon compound whose molecular formula is C8H18 was determined to have a given number of isomers. Define the term structural isomerism. Okay? So structural isomerism refers to when compounds, they have the same molecular formula. So this is the same, but they have different structural formulae. Okay, so they have the same number of atoms, so they would all have C8H18, right? 8 carbons, 18 hydrogens, but the structural formulae, the way that we draw them, right? The way that the carbon atoms are connected would be different. So that's what structural isomerism refers to. All right. So part 2 says list 3 types of structural isomerism. So there are 3 types of structural isomerism that we've covered in the CAPE syllabus, and these are the 3. So it's chain isomerism, positional isomerism, and functional group isomerism. So these all fall under the category of structural isomerism. Okay? Next, we're being asked to define one of the types of structural isomerisms that we just listed in part 2 here. And so the one type that I defined here was chain isomerism, so the first one. And that one refers to when isomers differ in the arrangement of the carbon atoms in their carbon skeleton, right? So in this type of isomerism, you might have like a carbon backbone, and then you have like a substituent hanging off, right? Like a methyl or dimethyl or something like that. But the backbone or the skeleton is different, right? Among those isomers. And then positional isomers, that would mean that the position of the functional group, so say it's an alcohol, right? The alcohol, the OH would be on different carbons in each instance. So that would be positional. And then functional group would mean that the molecule itself is comprised of a different functional group, right, in each instant of that isomerism, but they still have the same overall molecular formula, okay? So you can define any one of these that you want, but I just defined the simplest one here, which is chain isomerism, right? And that's the simplest one. And in fact, that's one of the main forms of structural isomerism that the CH818, which is an alkane, if you could tell based on that general formula there, CnH2n plus 2, that alkane, right, would be able to show chain isomerism. Okay, and so that brings us to the next part of this question now. So we are at 1B now. And 1B says that hydrocarbon compound, right, molecular formula C8H18 was determined to have a given number of isomers. So it's the same setup. Now we're being asked to draw 2 isomers that have 1 methyl substituent, right? So now what are we doing? We're drawing some chain isomers where we're changing up, right, that carbon skeleton between them, right? Same molecular formula, guys, but we're changing their backbone, the carbon skeleton. So here are 2 that we could draw. There are others that we could come up with, but here are 2 that I drew here. So first I drew 2-methylheptane, right? So what I did here is instead of the 8 being my longest chain, right, carbons, I have 7 carbons here. And then on the second carbon, I have my methyl substituent, right? So let me just highlight that here now is my methyl substituent, and that was a requirement that these isomers that we draw would have 1 methyl substituent. So here's my 1 methyl substituent, and it's on my second carbon. So let me just number them here. 5, 6, 7. Right, so I still have my 8 carbon, see? But there's 7 on this skeleton, and then there's a substituent that's the methyl where one other one is incorporated. So there's still 8 there. So that's my first isomer that has a methyl substituent. And here's my other one. I just literally moved the methyl to the third carbon instead of it being on the second one. I just put it on the third carbon, okay? So now this was 3-methyl heptane. And you can imagine a scenario in which you just move the methyl to the fourth carbon, and then that would be 4-methyl heptane, okay? All right, so all of these would be examples of chain isomers that we just drew here for this compound here, okay? And so we meet the criteria here that it would have 1-methyl substituent. So let me just circle my methyl substituent here again. Here's my methyl substituent. All right, and so we're good with that. 2 marks, so 1 for each of these structures. All right, so let's clear this, and we're gonna go ahead to the other part. So the other part says, okay, we're gonna draw 3 isomers now that contain only secondary and tertiary carbon atoms and at least 2 methyl substituents. So we have to think, how can I rearrange my carbon skeleton, right? So that I can incorporate 2 methyl substituents and I'll only have secondary or tertiary carbon. So let's just do a quick refresher on these, what this part means, right? For the secondary, we have to have a carbon that only has 2 other carbons attached to it. So this would be a secondary carbon right here. And you can imagine I have a hydrogen down here, but there's 1 carbon here and 1 carbon here. So there are 2 surrounding it, that's secondary. And then here's a carbon here. Let's say I put a H down here. And I have 1, 2, 3 carbons that surround that central carbon. So that carbon would be a tertiary carbon. So all the carbons that are in the isomers, the 3 of the isomers I'm going to draw, have to either be secondary or tertiary. There can be no primary carbon atoms in that structure, right? And then, of course, at least 2 methyl substituents. So, we're going to choose positions along the carbon skeleton where we're going to just tack on methyl groups. So here's what we came up with here. So let's look at this first one. So let's look at this first molecule here. So on this first molecule, I have my longest carbon skeleton being 6 carbons in length, right? So this is 1, 2, 3, 4, 5, 6. And on my second carbon, I placed a methyl. So here's 1 methyl. And then on my third, I placed another methyl, right? So in all, again, I have 8 carbons because there are 6 in the backbone and then 1 in each of these methyls. So that's 2,3-dimethyl-hexane. Of course, your N carbons are always going to be just primary. So we're not going to worry about those meeting this criteria. But the ones in the middle, so like 2, 3, 4, 5, they all meet the secondary, tertiary criteria. So let's look at this one here at 5. This one is connected to what? 1 carbon, 2 carbon. So that's a what? That's a secondary carbon. This one is connected to 1, 2. So it's a secondary carbon as well. That's carbon 4. And then carbon 3. Let's look at carbon 3. Carbon 3 is connected to what? 1, 2, 3. So that's a tertiary carbon. Carbon 2 is the same way, where it's connected to 1, 2, 3. So that's a tertiary carbon. So we've met that criteria, both of these criteria. So that's good. Similarly, we can do a similar thing where we have the same hexane backbone where there are 6 carbons there. And all I'm doing is just shifting the methyl. So here's a methyl that I have on my second carbon. And then I skip the third. And then on the fourth one, I have a methyl as well, just so we can get some variation in the isomers that we're drawing. They're just what? Chain isomers, right? So here's a methyl, we needed 2, so this works as well. All right, so then now I have another isomer in which I just shortened the carbon skeleton. So now I have 5 carbons in this one. 1, 2, 3, 4, 5, right? I put a methyl on my second carbon. I put another one on my third. And then I put another one on my fourth. Now they said at least 2 methyl substituents, so you could do more, right? You could do more than the 2, and that's what I did here. So now I have 3 methyl substituents. My backbone is 5 carbons, so what's that? 5 and 1, 2, 3, 8. So I'm still C8H18. And then let's check for the secondary and tertiary condition, right? Again, your end methyls are always gonna be primary. The carbons are gonna be primary, but the middle ones, let's check the middle ones, 2, 3, and 4, to see if they meet secondary and tertiary criteria, right? So if we look at the second carbon, we see that there's what? 1, 2, 3 carbons attached to it. So that's a tertiary carbon there. Let's look at this one. This one has 1, 2, 3 carbons attached to it. So carbon 3 is a tertiary carbon as well. Let's look at 4. 4 has 1, 2, 3. So that's a tertiary carbon as well, right? And so we're good, right? We've met both of these criteria, and so we're good for our 3 marks here. Now, there are other variations that you might come up with, but this is just an example of what was expected here, okay? All right, so let's go ahead now to the other part of this question. So let's clear this. All right. All right, so now we're at part C, 1C. It says that the scheme in the figure below shows a sequence of reactions that indicate the outcome of reacting an isomer of hydrocarbon A. Carefully examine the scheme and answer the questions that follow. Okay, so here's our scheme. We're starting with hydrocarbon A, and then we see that we have chlorine as a reagent, and we see that we have HV there. So that's UV light that's being present. And when we do that reaction with that hydrocarbon there, we get compound B. Then when we get compound B, we're going to add reagent X to compound B, and that results in us forming this structure here where we see that we have OH, OH. So this is a diol. We have OH on both ends, and then the rest of the molecule is just hydrocarbon, right? And so let's see what the questions are now. So we have to give the structural formula of compound A, 2 marks. We have to give the structural formula of compound B, and we have to know what reagent we're going to use to get from B to this final structure here. Okay? So there are a few things that we want to think about here in solving this puzzle, right? So let's start doing that now. So the minute I see that I have UV light here, right, and it's a hydrocarbon, it kind of tells me right away that this has to be some sort of a alkane, right, or a completely saturated hydrocarbon. Then one of the most important things here is to look at this OH here and this OH here, right? So that will give us some insight into what B needs to be, right? Because if I have a hydrocarbon and I'm adding chlorine to it, it means that I'm gonna form a haloalkane in the middle, right? And that would be an alkane. And then that haloalkane will undergo some kind of a substitution, right? A nucleophilic substitution to be exact, that will get rid of the halogens to give us these OH or these alcohol groups here. And so if we were to work backwards now, we're going to start with this structure, right? Because that's all we have from a structure standpoint. So let's work backwards now. These OHs that we got here came from chlorines being substituted out, right? So my B, the structure that I would draw for B is I would just draw this exact same structure, but substituting the CLs here, okay? So it would be CL, CL on that end where the OH ended up in the end, and then my H is still here, CH3, and then this part as well, but this would be a Cl, this would be a CH3, this would be CH3, right? So this is my B, this is B, it's a haloalkane, you see that? Dichloro, haloalkane, so it's a dichloro that we have here, right? And so that's what we would have here. And then now you know that these chlorines that got incorporated from here, right, would have been incorporated in an alkane. So just these chlorines are gonna substitute, we're gonna replace them with hydrogens because we're starting out with a hydrocarbon. So we know that these weren't there from the beginning. So it would have been H where those are. So we're just gonna drop a H there. 3, CH3, and then H, CH3, bam, bam, bam. Where that chlorine was, we know that the H would have had to have been there, that got substituted out, right? CH3, right? And so with that, we have compound A, right? That's a hydrocarbon, just carbon and hydrogens, completely saturated, so no double bond, so we know it's an alkane. We're gonna add chlorine and UV light, so that's gonna get substituted out. These hydrogens are getting substituted out to give us the chlorines on the end. If we need to go from chlorines, we need to replace our chlorines to get hydroxyl groups, then our reagent X has to be a strong base like sodium hydroxide that would supply these hydroxyl groups, right? And so immediately we've identified our X, our reagent X has to then be sodium hydroxide. And generally, we also have ethanol being used as a solvent as well. So you could have added that as well. So we use ethanol as a solvent for the haloalkane. Okay, because the haloalkane isn't soluble in aqueous solutions, and so we have to use something to put the haloalkane in solution, and that would be the ethanol. So this is just an extra. This is a solvent that we use, but the reagent that we actually need is the sodium hydroxide or any other strong base that can supply the hydroxyls that would substitute out the Cl. So it's remember again, it's a nucleophilic substitution that's going on. So we need a strong nucleophile to get rid of these guys in order to form this in the end ultimately. Okay, so we've identified everything, right? So this is compound A. This is the structure of compound A. This is the structure of compound B. And our reagent is sodium hydroxide, and the solvent that we're going to use is generally like ethanol for the haloalkane, okay? All right, so moving right along, let's go ahead now. All right, so it's saying now, list the names of the steps involved in going from A to B, right? So let me just quickly put up A again here. So we said that A would have been just a general alkane, right? So it would have been, let's put it, I'm going to put it here and then take it back down. CH3, CH3, H, CH3. We have a methyl up here. We have a H out here, and then CH3, right? That's the alkane that we started with. And so if we need to get to B using the Cl2 and the UV light, we got to B, we said that B would have been the chloroalkane. So we'd have had the H on the end being substituted out. And then CH3. CH3. We have a H here, a methyl down here, and then out here we have a methyl up here, a Cl here, and then the CH3, right? So this is what we have. So if we have an alkane, as we said earlier, and we need to get to a haloalkane, then the mechanism for that reaction is actually what we call what? Free radical substitution, right? So that's the name of the mechanism that would get us from A to B. So it's free radical substitution, and there are several steps that make up free radical substitution, and that's what we're being asked to list right here now. We have to list the names of the steps, okay? So the steps involving going from an alkane to a haloalkane in free radical substitution. So let's clear that and bring up the name of the steps now in free radical substitution. So the steps are step 1, initiation, step 2, propagation, and finally, termination. We list those 3 steps, we get our 3 marks, we're good. That's all that's required here. So now we're gonna go ahead and we're now being asked to use curved arrows to show the mechanism for the first step that we listed earlier. The first step that we listed earlier here, right, in free radical substitution was initiation. And so initiation, in that first step, what is happening is that we have the formation of chlorine radicals by homolytic fission of the Cl-Cl bond. So if I were to show that using curved arrows, which is what the question requested, I would draw my Cl bond. I would show the electrons that were shared there to form that bond. And then, because I'm forming radicals, it's a homolytic fission, which means that the electrons are going to split evenly or equally among each chlorine atom. So I'm going to use a half hook arrow. So I'm going to take this half hook, take this one, half hook. So one of my electrons is going to go and sit on this chlorine, and the other one is going to go and sit on this chlorine, and that forms, in the presence of UV light, that forms 2 chlorine radicals, right? And those 2 chlorine radicals are what are going to initiate, right, this, or continue the propagation, right? So we can substitute out the hydrogens that were in the alkane. Okay, so these radicals are what are needed to jumpstart the reaction. So that's how we show it from a mechanism standpoint. Remember your half hook arrows because you're forming radicals. And yeah, so that's all that's needed here for those 2 marks. So let's clear this and go ahead. All right. So now we're being asked to give the structural formula of a product that can be formed alternatively to compound B in C part 1 above, right? So compound B, we said that was the haloalkane, right? That was where we had the 2 chloro groups on the end here, right? So I had, instead of this, I had the Cl and then I had the Cl, right? That's what we had for B. So they're saying structural form of a product can be formed alternatively to that B, right? This hydrogen here that was in B, right? If I assume that I have a ton of chlorine, right? Then when I form the haloalkane, I could have replaced that hydrogen as well. So that's one structure that we can draw here to say that B could have been a compound that had 3 chloro groups instead of the 2 that we had shown previously. So that's a potential structure that we could put there. Also, you could say that these hydrogens in the methyls on the end, those are the ones that get substituted out with the chlorine, right? So that's a potential answer as well, where you're drawing chlorines here. So this would be Cl3Cl, Cl3, right? Cl3C. So that's a potential answer as well. So this one is really just up to your own interpretation and how you think about it. So what I did was just assume that there's excess chlorine available. And so instead of just having Cl, we have another Cl here in the middle where that hydrogen was, right? And so this would be the structure that I draw down here. Let me just go ahead and draw it out so you can see. Right, so it would have been Cl, CH3, CH3. I would have replaced this hydrogen now to be Cl, and then the CH3 would have still been down there, and then here now would have been CH3, Cl, and then CH3. Okay, So again, it's similar to what we had drawn for B earlier, but now we're saying, okay, I have so much chlorine that I'm going to substitute out the hydrogen that was in the middle, and it's going to become Cl as well. Okay, so that's a proposition here, 1 mark. Okay, so let's clear that. And then go ahead now. It says, given that ethanol has a pKa of 16, suggest whether the pKa of compound C is higher or lower than that of ethanol. So right away, I'm just going to draw ethanol right beside compound C so we can compare them, right? So ethanol is C2H5OH. So let's just put that here. This is ethanol. OH, right? And so when we think about pKa, pK is a measure of acid strength. And so when we think about the acid, it's a proton donor, right? The proton that it's going to donate is the proton that's attached to the OH, to the O. So it would be this one here. And in this case for compound C, it would be this one and this one. Those are your proton donors or your hydrogens that would be given off, right? In the case of if the alcohol were to act as an acid, right? So let's keep that in mind. And so here's what we can say then as it relates to what would happen with ethanol versus this compound C here. So compound C, when we look at compound C, we see that it consists of tertiary alcohols. We see that the OH is attached to a carbon that's attached to 1, 2, 3 other carbons. So that's a tertiary alcohol that we're looking at here and also here. Tertiary alcohols are slightly weaker acids than primary alcohol. This is a primary alcohol. This OH is attached to a carbon that's attached to only one other, right? So that's a primary alcohol. And these are going to be stronger acids than your tertiary alcohols. And so the weaker the acid, right? This is a weaker acid, the higher the pKa value is going to be. So compound C will have a higher pKa value than ethanol. Okay, so we can imagine that this one would have a pKa just slightly higher. So if this is 16 for the pKa, this one would say could potentially be something like 16.5 or, right? Slightly higher, or maybe even 17, right? But it's higher because it's a weaker acid. Remember, the lower the pKa, the stronger the acid. Okay, and so this will be weaker because of the tertiary carbons to which the OH is attached. Okay, so that's our answer here for 3 marks. And so let's go ahead, see what else is being asked. All right, so if the reaction of going from A to B was performed in a closed vessel, what would the expected color change be? What would be the expected color change? So if this is happening in a closed vessel, and we know that this is an alkane as we've already established, and it's in a closed vessel, what's gonna happen? There would be no color change expected since the light is needed for the reaction to proceed. And by closing the vessel, we exclude light. So there will be no color change. There will be no reaction, right? So there will be nothing there to see because the alkane, remember, a key requirement is that we have UV light because the UV light is needed to break the Cl bond to form those radicals to jumpstart the reaction. So without light, nothing will happen and we won't see a color change. 2 marks, done. All right, so this one now says in an experiment, 2 drops of universal indicator, right, very important, universal indicator were added to 1 centimeter cube of ethanol in test tube 1 and then 1 centimeter cube of compound C in test tube 2. Suggest the colors expected in test tubes 1 and 2, right? So a universal indicator is a solution. In this case, we're adding a solution. So it's a solution that's comprised of a variety of different indicators. And so it has a range of colors that it can give us. to tell us the strength or the nature of the solution that we're testing, right? And so from a color standpoint, these are some of the ranges of colors that we can see when we add a universal indicator to a solution, a test solution, right? And so if something is highly acidic, so a really strong acid, it will be down here in this range. And then as it gradually weakens, weak acid to becoming neutral, we would see these colors here. And over here is for highly basic, right? And then weakly basic. So earlier, we said we had a pKa value for ethanol. And we said the pKa value for ethanol, they gave us to be 16. So the pKa value for ethanol, we said was 16. And then we said the compound C, which is a tertiary alcohol, would have a pKa of around 16.5 to 17, right? And so what that means is that compared to like your organic acids like HCl, the ethanol is a very weak acid, right? So it would be somewhere in this region here, somewhere here in the spectrum. So this is like a yellow greenish, right? This is kind of where you'd expect the ethanol. You would see for the ethanol, it's a weak acid, right? But even weaker than it would be the compound C, right? Even weaker than it would be the compound C. And that compound C, so we would say it would potentially be here, right? Like a darker yellow green, that is what we would expect. They're both weak acids, so we don't expect to see them you don't expect to see these colors. These are very bright colors for these strong acids. These are weak acids, so we expect to see them here, right? Closer to neutral. And so let's go back to the question now to fill it in on this basis, right? So that would have been what color would expect for like compound C. So let us clear this and go back to our screen now. So in test tube 1 for ethanol, we expect to see like a yellow-green, right? Yellowish green there. And that would be ethanol, a weak acid. And an even weaker acid would be the compound C. And so that would be a slightly darker yellow-green or lime-green, right? Slightly darker yellow-green or lime-green. So those are the colors that we would expect to see. Okay? And so with that, we've come to the end of this question. Definitely give this video a like, subscribe to the channel, and if you look on your left here, you'll see the next video up. And if you look on the right here, you'll find our Module 1 playlist with tons of interesting content that will be helpful in getting you prepared for your exam. So thanks for watching, and we'll see you in our next video.